Welcome to our discussion on the law of large numbers. So the law of large numbers applies to any process that has a probability, and we'll call that the event is A, and then the probability of that event is P of A, right? So an event could be, flipping a coin, rolling a six-sided die, drawing a card out of a deck, um, being in an auto accident, right? There's all sorts of events that will then have associated probabilities. And the results of repeated trials must be independent. So in the case of flipping a coin and rolling dice, those are always independent. But in the case of like picking a card out of a deck, you would have to pick with replacement so that the next trial would be independent. Because otherwise, once you pick one, the next one's probability changes based on the card that you have, right? So if the process is repeated through many, many trials, the proportion of the trials in which your event occurs will be close to the probability of A, the theoretical probability of A. And the larger the number of those trials that you do, the closer your proportion should be to it. So basically what this is saying is there are two kind of types of probabilities. There's theoretical probability and then there's experimental probability. In theory, we know that if we flip a coin, we should see tails 50% of the time, right? 50-50. But in an experiment, we could flip a coin 10 times and actually get 10 tails, right? Be nowhere close to 50-50. But if we took that experiment of flipping a coin and repeated it 100 times, now we're probably going to have, maybe 55-45. Pretty darn close. And then if we do it 1,000 times, right? Maybe we're going to have like 503 and then 497. Now it's getting really close to 50-50. And then you do it 10,000 times. Maybe you're only off by one. So the idea is the longer you stretch out your experiment, the closer your results are going to approach the theoretical result. And that's basically what this graph is showing. So this was with die rolling, and it shows the results of a computer simulation of rolling a die, and then the proportion of ones, right? And we know that a one should show up 1/6 of the time. So there's 1/6 as a decimal, 0.167. And you can see that it started off really small, and then it got up pretty high to 2 at one point, and then it starts to come down. You'll have some little peaks and valleys, another little jump here, right? But as you go out more and more experiments, it's going to level off and it's going to get really close to 0.167, and it's pretty much going to stay there. That's the idea of the law of large averages, is that your experimental results will always tend towards what the theoretical says it should be. So here's another example. A regulation roulette wheel has 38 numbers, 18 of them are black, 18 of them are red, and then you have two green numbers, 0 and 00. Assume that all possible outcomes, the 38 numbers, have equal probability, which you should, because the wheel, they should all be the same size, unless somebody's cheating. What's the probability of getting a red number on any spin? Well, on any given spin, probability is always good over total. And if you want red, then red are the good, right? And there are 18 red, so that's your good of 18. And then the total is just the 38 total numbers. So good over total gives you 18 over 38, which reduces to 0.474 as a decimal. Okay, so if patrons in a casino spin the wheel 100,000 times, how many times will a red number be the outcome? Well, an expected value is what you would expect to see on average over the long term. And in simplest terms, we always compute expected values by simply taking the probability of that event and multiplying by the sample space. So you would literally just take 0.474, multiply it by 100,000, and you would think that out of 100,000 rolls, you should see 47,400 times the wheel will come up red. Now that's not guaranteed, right? Because that's still theoretical and experimental. All sorts of weird things can happen. But in 100,000 rolls, right, spins, it should be pretty darn close to this. I mean, even if it's off by 10 or 20, that's a pretty small amount when you're talking about numbers as large as 47,000, right? So Let's consider two events, each with its own value and probability. So the expected value equals the event 1 value times the event 1 probability plus the event 2 value times the event 2 probability. And this formula, we can expand it out to include a large number of events with their included probabilities, right? And so you can always find the expected value of any scenario or game or whatever that has multiple outcomes, as long as each outcome has a value associated with it, and then each outcome has a probability associated with it. And this is what insurance companies do. This is how insurance companies figure out how much money to charge you for a policy, because they figure out the probability of something happening to you that will cost them a certain amount of money. They multiply those together, and then the probability of something happening to you that will cost them a different set, and so on and so forth. And they add all those different things together, and that comes up with the expected value of what you would cost them in the long run, and then they make sure to charge you more than that. So suppose an automobile insurance company sells an insurance policy with an annual premium of $200. Based on the data from past claims, the company has calculated the following probabilities. On average, 1 in 50 policyholders will file a claim of $2,000, 1 in 20 will file a claim for $1,000, and 1 in 10 will file a claim of $500. Assuming that the policyholder could file any of the claims above, what is the expected value to the company for each policy sold? So it's very simple. The expected value is, well, 200 times its probability, and its probability is 1, since you have to pay $200, right, to get the premium. And then negative 2,000, because they lose 2,000, and the probability of that happening, they said, was 1 out of 50. And then negative 1,000 times 1 out of 20, and then negative 500 times 1 over 10. And if you do all that math, it comes out to $60. So this suggests that if the company sells a policy for 200 bucks, on average, they should make 60, right? Some people will cost them more money because obviously, these people are costing them a lot of money. The 2000s, the 1000s, the 500s, when they only paid $200 for a premium. But all the other people who didn't make any claims are basically just giving them $200. And so it averages out that they make $60 per policy, and therefore they would want to sell as many policies as they can. Now, the gambler's fallacy comes from this idea of expected values and the law of large numbers. It's the mistaken belief that a streak of bad luck makes a person due for a streak of good luck, right? Because they know that in the long run, things need to average out. So for instance, if you're sitting there and watching the roulette wheel, right? And it comes up black, 15 times in a row, you're thinking, well, crap, it's got to come up red eventually, right? We know that it has to hit black and red almost 50-50. We saw that it was 0.474 because of those two stupid green things. So if it's been black 15 times in a row, well, the next one's got to be red, so I'm going to bet the house on red. And what happens? Whoop, comes up black again, right? Because the wheel doesn't know that it was black 17 times or 15 times in a row. Each spin is completely independent, so there's no reason why the next spin should be anything other than the same chances, right? It still has a 0.474 chance of being red on the next spin. It still has a 0.474 chance of being black on the next spin, and it still has whatever that leftover bit is of being green, right? So that's the gambler's fallacy, is they think when they see a streak, the opposite must happen, because they know in the long run things are supposed to even out. But the long run is just that. It's the long run. And when we're talking, tens of thousands of things type of thing, and not just the next time they play the game. So suppose you're playing the coin toss game, in which you win $1 for heads and lose $1 for tails. After 100 tosses, you are $10 in the hole because you flipped 45 heads and 55 tails. So you keep playing the game. You continue playing until you've tossed the coin 1,000 times, at which point you've gotten 480 heads and 520 tails. Does the result agree with the the law of large numbers? Have you gained back any of your losses? Well, obviously you've now made $480 for those, and then you've lost 520 for tails. You're now in the hole by a difference of $40, right? You were down by 10, now you're down by 40. So you've played the game more and you've lost even more. So you would think this is not following the law of large averages. But remember, the law of large averages will have peaks and valleys until you get way out there with really large numbers. And 1,000 is not really a large number in the grand scheme of things. So even though you lost more money, this is still following the law of large numbers. It just hasn't evened out because you haven't played it, 100,000 times. And then at that point, you should pretty much break even. So again, with the gambler's fallacy, it's the idea of streaks. For tossing a coin 6 times, the outcomes of this and this are equally likely. They have the exact same probability. So whether it comes up heads, tails, tails, heads, tails, heads, or 6 heads in a row, those two things have the exact same probability of happening because it's basically a 50-50 chance of getting heads, a 50-50 chance of this, right? 50-50, 50-50. So it's 1/2 times 1/2 times 1/2 times 1/2, 6 times, which is 2, 4, 6, sorry, 2, 4, 8, 16, 32, 64. Both of those all have a 1/64 probability. And you think, how can that be? Well, that's just the way probability works. Because again, the coin doesn't have a memory. It doesn't know the first flip was heads. It doesn't know the second one was heads, right? So every time you flip it, it's still a 50-50 chance that it comes up heads. And that's why gamblers lose and Vegas makes so much money. Okay, a farmer knows that at this time of year in his past, in his part of the country, the probability of rain on a given day is 50-50, 0.5. It hasn't rained in 10 days, and he needs to decide whether to start irrigating. Is he justified in postponing irrigation because his region is due for a rainy day? No. Just because there's been 10 days of dry doesn't mean it has to rain tomorrow. It's still a 50-50 chance of raining tomorrow. So it's unexpected to see those 10 days of dry spell and think of that as a losing streak, but the next day still only has a 50-50 chance of raining. And this is where you get, the house edge, the gambling house, the casinos. That's why they make money. Not only because of all these gamblers' fallacies and things like that, but they've set up the games so that the house always has a higher probability of winning. Not all games, actually, single deck blackjack, under certain circumstances, the player has a slight edge. But the vast majority of games out there, the house has a slight edge. For instance, in roulette, you as we saw, you only have basically a 0.474 chance of it coming up red or black. However, when you make that bet, it's a 2-to-1. So it's a 50, it's a 1-to-1 thing. It's a 50% thing. So if you bet $1, you win $1. And the idea of that is if it's a 50-50 thing, then it should even out. But as you know, in the long run, yes, it's going to come up black and red evenly, so you're going to lose as many times as you win, but those two green ones are also going to show up, which give the house just enough edge so that you just lose a little, right? You lose enough so that you don't win. So you can't just sit there and bet black over and over and over again, knowing that it will even itself out. It won't because of the greens. And that's how the house always wins.